Oke, Assalamualaikum warahmatullahi wabarakatuh. My name is Neo Safitri, NPM 2013-022-006. Study Program Physical Education Class B. Work by a constant force. Suppose an object and apply a constant force in the horizontal direction. Concept of work: suppose the force starts at point x initial and goes to position x final and calls it the direction I. Formula can be written: first those objects force equal fx dot I. Displacement of these objects delta x equal delta x dot I. So, the vector of displacement is delta x equal to xf minus xi. Delta x equal xf minus xi. First, for the case where fx is constant, the definition of work done by the force in moving the object from the initial position to the final position is the product of the force fx time the displacement equals fx times xf minus xi. This is the definition for cases where force is constant. If the force fx is less than 0 and shift in the positive direction, then the work is negative. If the force fx is positive and the displacement is positive, then the work is positive. Work is the product of force and distance. SI unit, the unit of force, which is Newton times meter, equal joule. In the first graph, the x component of the force has some origin as x. Starting from xi and xf, and during this process it assumes that the force is constant, so make a shadow in this area. That our work is the product of force and displacement. This is a working example for constant force. Video 2. Work by a non-constant force. The case playing force F is a function of x, so the component of fx is a function of x towards I hat. The simplest example of this force is called the spring force. Now we apply this style to the object. This is our positive x coordinate system. We apply force is function of position, so look at the displacement in a small amount, so let's call this the point xi and this is xi plus 1. How much work droppy when the force is from here to here, and that's what's called delta x. So our displacement is delta x equal to xi plus 1 minus xi. Job for this displacement, why do we show with delta y equal to first f a function of x times displacement, so you get fx xi plus 1 minus xi. If we want total work, we have to add I equals 1 to n fx of I delta xi. Delta xg. What does the number mean? That is what defines as work from in constant style. The problem here is about how well we cut their intervals, so what is the limit since and becomes infinite, it needs to be considered. What we're doing is making the displacement smaller and smaller. And take this sum g is equal to 1 to n fx of g times delta x g. And its summation limit is by definition the force integral with respect to the x prime. So work is an integral of fx. A function has an integral variable x prime of the x prime, where x prime moves from the start to end position to the end position. From this figure, it is now a working definition that generalizes a constant to an inconstant force. Plotting fx versus x, plotting the force as if it were increasing as a function of x. Here xf. We're going to make a geometric interpretation considering xg to be really big, xg plus 1, and the value here is fx of g. So what we see now is that is little effort as for constant force can be approximate to the area under the curve only for the small interval between xg and xi plus 1. Now you see graphically that there is a slight error when the function is almost constant, but where does the function develop? That's our fault. But within limits becomes infinite, so that the error becomes smaller. One more area under the first versus position curve between initial and final. That's our generation of the definition of work. Okay, next, kinetic energy. The kinetic energy K is equal to half mv squared. That is a scalar quantity, so be zero or positive. The S1 unit for kinetic energy is the joule derived from the kilogram meter per second squared. Suppose we have an object that is first it rests and then accelerates at a certain speed. It means that the object is experiencing a change in kinetic energy. The change in kinetic energy is equal to half mvf squared minus half mvi squared. If there is movement, the speed enters, say, 20 or 30 space. Then half m10 vxf squared plus vyf squared plus vzf squared minus all initial values xi, yi, and zi. How to install momentum and kinetic energy? So K is equal to half mv squared, remember. P is equal to mv. So equal P squared is more than 2m. That is the kinetic energy expressed in terms of the particle momentum. Next, work kinetic energy theorem. Let's derive the work energy principle. Use Newton's second law, but not with time but with space. Second law, so F is equal to ma taking the x component from it. No, we're going to integrate this, so fx dx prime goes from x prime to xf and x prime to xi. M integral runs the initial value to the same ending value and has ax dx prime. The values entered here get half m vf squared minus f1 fi squared. This is change in kinetic energy integral fx dx we call y, and the work on that system is the change in kinetic energy, so this is the principle of work energy. Okay, thank you very much. See you. Wassalamualaikum warahmatullahi wabarakatuh.